Swayam Prabha. Digital India. Educated India.
Yeah. So remember, gradient descent, the simple idea is it's an optimization algorithm. This is important to remember. In between all these, there are a few moving parts, but all gradient descent is if you give it a function to minimize, it's supposed to minimize it. So the way to do it is to start with some random initial guess. In our case, in the case of neural networks, we are basically X here denotes the weights that we are trying to minimize. We are trying to minimize. So that's what typically we denote it by W. Um, so we decide on some positive number alpha. Um, uh, Typically it's a small number. And then we iterate this simple equation. That is, you just take the gradient of whatever function we wish to minimize. We called it J, but in general optimization literature, it will be F. But or in our least square case, we called it S. It's just a simple objective function that you want to minimize. And then you iterate till a pre-specified convergence limit. So automatically it is stopped in case you need grad f equal to 0. This we saw last time. So once again, the equation is you search in the direction minus grad f, which is why it's called gradient. And since it's minus, it's called descent. And alpha is a positive constant. You can write other types of optimization algorithms by manipulating this lambda and by manipulating S. We are not going to do that because optimization is not the mainstay of our course. So idea is to start on alpha and epsilon, the stopping criteria, make an initial guess, iterate wk plus 1 equal to wk minus alpha grad j, and you decide on the stopping criteria, and if you are satisfied you stop, and if you are not satisfied you go back and calculate the gradient again. Okay, so again, once again I'll ask you to go to oops, just one second. So you can take a look at this question. But please try and go to item pool and just answer the question. It's just related to this. I want to show you just one iteration of this question. So where am I hope all of you are able to see this question now. Just answer for one iteration. I'll show you the case of other iterations later. Is everybody able to see it? So for those who came a little bit late, please go to itempool.com/balaji/live. Okay, I have about 35 answers. So almost everybody has gotten it right. Let me just, I don't have to explain it in too much detail. Somebody might have just made some small calculation error, but nonetheless, let me just show it. Yeah. So all we need to do is we need to find out grad f. So del f del x1, del f del x2, so x1 minus 2 by x1 square, x2 is del f del x1, and minus 2 by x1 x2 square plus 6 is del f del x2. So at 1 1 this gives the value grad f at the initial position 1 1, gives us minus 1 and plus 4. So if we multiply by a rate of 0.05, so this is w goes to w minus alpha times grad f. So this becomes 1.05, and 0.05 is 2, so this is 0.8. Okay. So this is the new W. So this was original W, and now this is new W is this, and so on and so forth. We can keep on iterating. I hope this is clear. If somebody has a question, please do ask me. I'll show you what it looks like. So again, I'm just plotting the contours of this function. So we started from this point, which was 1, 1. And the next point is, you can see it's 1.05 and approximately 0.8. And these lines represent the contours of the function. You will notice roughly, okay, locally, each of my movements is perpendicular to the contour. Okay, as I explained in the previous class, the idea of gradient descent is to move perpendicular. Of course, the right direction to move from here would have been directly this way. Okay, so this is the final answer. This is the final optimum. You want to move in this direction, but we cannot see that far. We do not know how the function curves. Okay, remember, you only have one information here, or two pieces of information, the local function value and the local gradient. So you move the best direction you know how. This is sort of local optimization on how we deal with our lives also. You can locally look at what options you have, and you can choose the best option that you have locally. That might not be the global best step, but this is the local best step. And after a few iterations, you reach. So you can see how it progresses, 1.05 to 0.8 and 1.11, so on and so forth, and we will reach the optimum. Okay, so this is well and fine when we have a simple function like this, but how do we do an example of this sort? Okay, so let us say once again we have this one-dimensional steady state heat conduction in a slab. Okay, now remember how we found out the optimal line there. We put a linear model. We said that we will assume the temperature, and I'll use my notation. Y hat or T hat is, we said something like A plus BX. I'm going to say W0 plus W1X. This is our model. Where did we get this model? We got this model from solving the differential equation. But as we will see on Monday, we can simply use blindly, we can use a neural network and try to fit it, regardless of the fact that we don't know the physics. Okay, but of course, you need a lot more data. Since we already know a linear model, we need only a little bit of data. So we have this data of X versus temperature, which is given. Okay. And what I do is I set up, okay, you set up S as sigma of T actual minus T fit square, or T hat square, or Y hat square. In my notation, I call it sigma of Y minus Y hat square. And we wish to minimize this and find out W, minimize this gap. You can have a 1/2, or you can have a 1/2 times number of points. All these things don't make too much of a difference. They are just a little bit simpler when we want to differentiate. Okay, so you can look at mean square error and say, I want to minimize this, find out my weights, which will minimize this. So traditionally, as you saw, even in the last class, I projected this. All we do is, we do all this calculation of A and B directly, analytically. The question now is, how will you do this using gradient descent? So I would give me ideas on how we can do this using gradient descent. Just 1 second, I'll stop the share and I'll restart it. Yeah. So ideas, what would be the difference when we do things with gradient descent? Okay, so before I go to the general question, can you tell me what is the function we are minimizing?
Error function.
Sum of errors.
Okay, so how do we write
squares of errors?
Sum of squares of errors. J is equal to So I'll write it explicitly. Okay, so we have these serial numbers 1, 2, 3, 4, 5, 6. So let's call this I. So I will say yi. This is y. Let's call this as xi. Here you have yi. Yi minus what?
axi plus b. Yeah.
You can say, I am going to say my notation w0 plus w1 xi. This whole thing square. We will call this y hat I. Is everybody clear about this? And we will sum this up from y equal to 1 to 6. Okay. I'll put a factor of 1 by 2 here just for convenience. Oops. I'm putting a half here just for our convenience. Okay, so this is the function that I wish to minimize. Now, if I want to do gradient descent, what should I start with first?
Initial guess.
Yeah, an initial guess. Very good. So we need an initial guess. So I am going to give a really bad initial guess. So let's say initial guess is W0 equal to 0, W1 equal to 0. Okay, so we will start with an initial guess of 0, 0. Okay. What else do I need now? Apart from this,
Learning rate.
the learning rate. Okay, so let us say I am giving you alpha is equal to 0.2. Okay, what do we have to get next?
Tau j by tau w0 and tau w1.
So we also need del j by del w0. We need analytical expressions for these. Del j by del w1. Can all of you just try and calculate what these are? Anyway, you would have done it once to find out A and B also, but can you just find this out? What is del j by del w0 and what is del j by del w1? What are the expressions for these? If someone has it, you can just unmute yourself and tell me. I'll write it down cleanly. J is equal to half of sigma over I yi minus y hat I square. It is the same as half of sigma over I minus w0 plus xi. What is del j del w0? Anyone?
Del J del W0 is summation minus yi plus W0 plus W1 xi.
Okay. How else could you write it? Summation del J del W0. How did you calculate it? Okay, so let me just give you a easy way of doing so. So this is differentiate this. So 2 times this, which is yi or minus yi. I will write it the other way. It's just easier to differentiate. It's the same thing. It's a square, so it doesn't matter in which order I write it. So when I differentiate del J del W0, this is the same as del J del y hat del y hat del W0. So when you do that, these 2's cancel. You get 2 here. You get y hat, sorry about that, y hat I minus yi multiplied by del y hat I del W0. Everybody agrees with this? Similarly, this is going to be I y hat I minus yi del y hat I del W1. Okay. Now y hat I is equal to W0 plus W1xi. So this means del y hat I del W0 is 1. And there is a reason why I'm doing it this way. I want to tell you something else. Is xi. So what you should get is sigma y hat I minus yi, and you should get sigma y hat I minus yi times xi. Does everybody agree with this? Any questions? And I did the algebra a little bit fast. It should not be very complicated. Questions? Is everything clear? Okay, so here is what we are seeing. We are seeing that W0, yeah, sorry.
Sir, excuse me, sir.
Yeah.
Shouldn't it be minus xi for the dou j by dou w1?
No. See the derivative. Why do you think it should be minus x?
Yeah, because there is a minus term in the j expression. Y minus y not hat.
Yeah. You notice I have switched the order. It is y hat minus y.
Oh, okay.
So that's why I rewrote it as y hat I minus yi square, because it's a square. I can rewrite it that way. So when I differentiate it, this stays in this order. Okay. So several things here. I mean, actually, these expressions themselves are well worth paying attention to. I mean, rather than just seeing something as a result of a differentiation. See, if you notice, this is simply the error or the negative of the error, however you wish to look at it. This is my predicted value and this is my actual value. So what this tells us is the first del J del W0 is just the summation of the error. Okay. Del J del W1 is the summation of the error weighted by the variable x. Okay. Just in case, now remember I had talked about this case where instead of a linear fit, if we wanted to do a quadratic fit, and I had y hat I equal to W0 plus W1 xi plus W2 xi square, what would I have had to do? What would be del J del W2 now?
Summation of error into xi square.
Summation of error into xi square. So now that is easy. Now remember, if we have to solve for A, B, C here, you have to get more and more complicated expressions. A, B, C will change, but our gradients change in a very, very systematic fashion. Okay, it is very easy to program in. Third thing, instead of this, suppose I had two variables instead of having just x. Now I was doing linear regression in two variables and I had x1 and x2. Okay. So my model is y hat is equal to w0 plus w1 x1 plus w2 x2. Then what you would have here is del j del w0 would still be y hat I minus or error. The second one would be error times x1 of the ith data point, and del j del w2 would be error multiplied by x2 of the ith data point, and I can extend this to how many ever variables I have. So this is the power of writing in terms of the gradients. The first advantage is that regardless of whether I am doing a linear fit or a quadratic fit or a cubic fit or an n-dimensional fit, I can simply write all my gradients as error multiplied by whatever is the feature. Okay. Remember, I used the term feature last time. Again, I will not use this in too much detail later on. I am just pointing out where the advantages are, because we will see that it takes a long time to converge, unlike the straight expression. Obviously, if you have a single variable, the best way to do it is the direct method. But if you are not dealing with a single variable and you're dealing with multiple variables and you're dealing with very large problems, gradient descent starts getting powerful. Okay. This is sort of like an analogy with Kramer's rule. Kramer's rule is very powerful for a 3x3 system. Even when you start with 4x4 system, it sort of starts losing its power. By the time you go to 6x6 systems, it's probably the worst method that you can use. On the other hand, Gauss elimination or other methods are not so powerful when you deal with 3x3, but they become very powerful when you implement them on computers for large systems. So similarly, gradient descent is not a powerful method for the kind of examples we can afford to do in class or in the exam. But in actual practice, if you actually compute it, it becomes very, very powerful. So if we look at our algorithm, it becomes like this. Whatever our initial W was, this is going to be minus alpha times summation of y hat I minus yi, and W1 is going to be W1 minus alpha times summation of y hat I minus yi times xi, weighted by the specific feature that this multiplies. You can kind of imagine if I am doing a quadratic, then I will get W2 is equal to W2 minus alpha sigma of y hat I minus yi times xi square. So that would be an additional equation. In our case, we are going to look at only these two. Okay. So, and remember, I started with W0 and W1 of 0. I will just show you what it looks like. Okay. So this is the case where this is just one iteration. W1 is 0. Okay. So this is our X. This is our Y. This is our Y hat. Obviously, since W0 and W1 are 0, then Y hat is equal to W0 plus W1X, regardless of what X it is, I am going to predict 0. Okay. Now, Y hat minus Y, we have calculated it here. In this case, it's the same as minus Y. Now, what we needed was del J del W naught. This is sigma of Y hat I minus yi, and this is minus 78.26, and del J del W1, I have also done this calculation, X multiplied by Y hat minus Y. I will request you to do this by hand once, because something of this sort I could probably ask in the exam. I haven't checked the question paper, but I could possibly ask. Okay, so this comes to minus 0.5184. So this means W naught equal to W naught minus alpha, which is 0.2, multiplied by minus 78.26. How much does this come to? Can somebody calculate this and tell me? Sorry, 15.65. Okay, thanks. So W1 is W1 minus alpha times, this is not minus, I think this is, how much did I write? Oh, sorry, not 0.518. I wrote that incorrectly. Minus 2.59. I think now it should come to. So this comes to, I think, 0.5184. I am right? Am I right?
Yes. Yes.
Yeah, yeah, this is 0.5184. So this is the result of one iteration. And we know that the iterations have not ended. How do we know that the iterations have not ended?
Calculate J again.
You don't need to. So actually, to determine whether the iterations have ended or not, you don't even need to look at J. I can tell you just on the basis of the calculations we have done so far, the iterations have not ended. Based on what values can we say this?
The gradient.
Correct. So if you look at the gradient, these are very high. What do we expect it to be close to when we are nearing the minimum?
0.
Yeah, we want it to be very small. We want it to be close to the minimum, means it should be close to 0. Another way to look at it, which is equivalent really, is that W0 and W1 should not change too much across two different iterations. So this was initial. This is my second iteration. Is this clear to everybody? Based on both these criteria, which are really in some sense equivalent criteria. See, W0 will change a lot in case gradient is high. Okay, so we either look at how much W has changed or we look at the gradient directly. If we say something like gradient is less than, or the absolute value of the gradient of each of the components is less than 10 to the power minus 5, then I know that I can stop. Something of that sort we could do. So what I will do now is try and, any questions so far? So you can imagine that you will now have to repeat this any number of times in order to get to convergence. So I want to show you a couple of things here. Yeah. So I have here a code which basically I have written the whole thing up. So I have set the learning rate here. This of course is our input data, 0.01 through 0.06. This is our temperature data, 15.46. You can see that I have simply entered the values. These are the temperatures. Forget this line, I'll come back to this later. Just add a comment here. So this is our initial guess, 0, 0. Now, when I say this number of epochs, it simply means number of times I am going to do the iteration. I have given a large number of iterations. I will tell you later why I did that. But here is what happens. I defined y hat as W0. Well, in MATLAB, my indices start with 1, so I have to make it W1 plus W2x. dy is our error, which is y hat minus y. This is the cost function, but we are more interested in the gradient of the cost function, which I have called dj. So dj is simply the sum of dy. dj1 is simply the sum of dy, or dj0 in our terms, and dj1 is the sum of the error multiplied by x. So there is this dot star which will do an element wise multiplication, and I have taken the sum. And I have simply said that the new W is the old W minus alpha times dj. And it will, if you notice here, it will keep on writing what this new W is. Okay, what I want to do, let's, oops. Where is the next one? So if you see here, this is my initial line. 0, 0, and these are my data points, right? And as I continue to run it, you will see that it is adjusting. Now, it might not seem like too much of an adjustment, but you'll see my values are changing here. Okay, so you see now we started with 15 point something, we have ended up at 13.0302, etc. What I'll do now is to run it. It might take quite some time to run, so I'll not bore you too much with that. I'll show you another iteration method. So you can see it is slowly changing. I'll suppress the plots. Actually, let me show something else. Let's see how long it takes to run. What happened here? This should not have. The code is correct. What were the values which were there originally? Yeah. So let me just show you. So you can see when we did it using the usual method, we got B of 15.97. B, remember, is W0, and A of minus 83.80. These were the rough values. Remember, A is W1. So 15.97 minus 83.80. So if I see here, you can see 15.97 minus 83.91 something, and this happens to be more accurate because I think whoever did the previous problem rounded off. So you will see that we have gotten here. Okay, we have gotten to the actual value. Let me see if I can plot this and show you what it looks like. It's a fluff. So I am. So this is kind of. Let's see. I'll show you another result. Sorry, I'm unable to locate it. Yeah. So don't worry about the excessive thing that you see here. Let me just zoom in. So you can see the fit is pretty good. Okay. So this is what we did, but it took gradient descent a long time to reach here. Okay. On the other hand, I'll show you a small trick. Okay. So this is a useful trick. I might or might not talk about this later again in the course, which is, remember, we have our data which goes from x is 0.01 to 0.06 and t goes like this. But there is no reason why I cannot renormalize my data. Renormalize my data meaning, suppose I called, instead of x in meters, suppose I called it in centimeters. Okay. Then I would say x is going from 1 through 6. My constants will change, but nonetheless, I am solving the same problem. Now, a good way to do almost all machine learning tasks, especially if you are using gradient descent, and there are multiple variations of this further on in sophisticated algorithms, is to always try and express your input data in the range 0 to 1. Okay, so that you re-normalize your data. That is, you do a linear transformation on the data and then keep it between 0 to 1. Okay. So the way you can do it, is I can simply say x goes to x minus minimum of x by maximum of x by minimum of x minus minimum of x. If you do this transformation, what happens is x now rescales to between, you will see now, X was originally between 0.01 to 0.06. Now my X is between 0 to 1. Okay. So now what I can do is, if I reduce the iterations to, let us say, 30. And oops, this is a problem with my plotting. Just 1 second. It should work fine. So you can now see that it has readjusted itself very, very well, even within just 30 iterations. So this is the power of normalization of data. What took, I actually iterated a lot with the original set of data. So what took a lot of time with the previous description of X, which was between 0.01 to 0.07, takes very little time when you renormalize it and say that X is between 0 and 1. There are multiple reasons for this. If you have some questions, you can ask me. But some of it is mildly complicated, but nonetheless, I would like to stop here. In terms of description of gradient descent, I have just one more slide to show. But if you have any questions, please do feel free to ask. And then I'll go back to just one more slide of my presentation. Questions?
Is this normalization only done for the independent variables?
Yes, it is typically done only for the independent variable, and then there is something called batch norm, which is done for all the intermediate layers also. But you don't necessarily have to do it for the output variable. You can if you wish to. Depends on what type of output variable you are dealing with. In linear regression, you can do it for the output variable too. In non-linear problems, you have to be careful.
Oh, okay.
Yeah. Other questions? Okay. So everybody gets how you do gradient descent for these sorts of problems, right? You simply calculate. What happened to all the stuff that I had written? It's very weird. Yeah, I don't know what's happening with Zoom. I see different versions of my file. Okay. Yeah. So finally, what we saw here is that for gradient descent, obviously you need to calculate the gradient. Now there is a problem when it comes to numerical techniques for neural networks. Generally, you won't have explicit expressions. In this case, we could calculate it very nicely. It can happen due to two reasons. Either you have J only as a black box. Okay, what I mean by that is, let's say you have a CFD computation and we are trying to do a heat transfer computation. We are trying to create a neural network surrogate model for something like, if you give me locations, I will give you output temperature. But unlike our case, we don't have an explicit clear model. Okay, in that case, this becomes difficult. Okay. And what is usually the case is that we have something like a neural network. So layer 1, layer 2, layer 3, layer 4. By the time you write down the function, it will look really, really, really messy. And it's very difficult to compute by hand for sure. Okay. So in both cases, the simplest solution really is the inference method. What do I mean by that? Suppose I have some weight del J del W0. What do? I took the W0 and W1 as 0 and 0. Now I take W0 as 10 to the power minus 5 and W1 as 0. So I perturb only W0, then find out how much J changes, and that's literally the meaning of del J del W0, which is change W0 by a little bit. Okay. Only that variable we perturb and then calculate it. Okay. Now, this is the simplest way, but this is not necessarily the most efficient way. What is the reason? The reason is that in a neural network, just imagine, even in the simple neural networks I showed you, you will have close to 100 weights. Now, for each iteration, you will have to perturb each weight. Okay, because W0 has to be perturbed to find out del J del W0. W1 has to be perturbed to find out del J del W1. And what do you have to do? You have to do 2 forward computations for each del J del W you want. Okay, one for the W0 W1 and then for the perturbed one. Even if the forward computation, the unperturbed one is common, you have to do 1 extra computation for each additional variable Wj that you have. If you have 100 weights, apart from the simple Wj calculation, you have to do 100 more calculations in order to find out all the perturbations so that you can evaluate these gradients. It also turns out that these are somewhat noisy. And this was the reason why, in fact, neural networks research was stuck for a long time. Okay. If the number of features and the number of weights is large, this becomes very expensive. Okay. However, there is a way of calculating in an implicit fashion. Okay, so this is something called automatic differentiation. Okay, I am not going to get into it. I'll very briefly describe how it is done on Monday. Okay, for neural networks specifically. There is a cheaper way of computing it. I call it a numerical way, but it is not numerical in the sense that it is not approximate. What we do is we find out the exact number that will come for del J, del Wj, but we do it just in terms of the number. I'll show it to you. It will become clearer when I show it to you on Monday. Basically, if the function is x square, it will always give me 2x without actually analytically calculating the 2x. So it will always give me, so if you say x is equal to 3, it will say derivative is equal to 6. If you say x is equal to 4, it will say derivative equal to 8, but it will never give you the full expression explicitly. Okay. So this method is called backpropagation, and that is the final piece that you need in order to understand how neural networks are used. So we will very briefly, automatic packages exist, you really don't need to know it, but since we are doing machine learning, I will just give you a brief taste of how it is done on Monday. So amongst the things that we have covered, what we have understood is, at the very least, if I have a linear model, I need to find out the error. I need to differentiate it with respect to the weights that I wish to discover, and then I will update the weights as W equal to W minus alpha times grad J. Okay, so W equal to W minus alpha times grad J with respect to W. So this simple thing with multiple iterations, you can actually get to the minimum, the same as how you did with your analytical technique. Okay. So on Monday, we will go ahead and see backpropagation, and our portions for the quiz will be till whatever I do on Monday. So any questions, comments?
Sir, is there any difference between gradient descent and steepest descent, or are they the same?
There is a Cauchy steepest descent. Cauchy steepest descent is slightly different from gradient descent. Okay. Very, very slightly different from gradient descent. Some people call gradient descent steepest descent. In machine learning literature, it is called gradient descent. So since you asked, you remember this learning rate? This
Yes,
learning
sir.
rate is set arbitrarily in gradient descent. There is a specific way of setting it in Cauchy steepest descent. Okay, that's
Okay.
all.
Okay, sir.
That's the difference.
So when we talk about this gradient descent, can there be any such situation where the function kind of like gets stuck in a local minimum?
Yeah. It happens all the time. So obviously, gradient descent, first of all, doesn't guarantee you convergence itself. Okay. Now, second thing, even if you converge, you might not converge to a global minima. Okay. You can get stuck at the local minimum. This is entirely possible in gradient descent, and in fact, it does happen very, very, very often. Okay. So can get stuck. at local minima. Now, this doesn't happen for the linear regression case. Why?
Linear regression is analytical, sir.
No, you can have an analytical function. It can get stuck with any sorts of things. Okay. It can
Only
get stuck.
one minimum.
There is only one minimum. Okay. That is the correct point. The right point is that in case of linear regression, you have only one minimum. It's a square function, and its shape is like this. Only one minimum. In 3D, its shape is like this. It looks like a parabola. So these are what are called as convex optimization problems. So in case of convex optimization problems, you will not get stuck in local minima because the local minimum is the global minimum. Okay. Otherwise, there is no guarantee whatsoever. So people have tried all sorts of techniques. If you have taken the optimization course by Professor C. Balaji, last year I didn't do these alternate techniques. So things like genetic optimization, etc., exist in order to perturb them out of local minima. Okay, so even machine learning people use something called evolutionary strategies nowadays, which is somewhat related to genetic algorithms for very similar reasons. Yeah, but in general, there is no guarantee. You can get stuck at local minimum. That's a good question. Yeah.
Thank you, sir.
Okay. Any other questions?
Sir, could you also upload the slides for the first two lectures?
For the first two lectures, I will myself have to locate them. So once I locate them, I'll upload them. But this one I will. That's why I do it immediately. Otherwise, I tend to kind of lose where my slides are. Yeah, I will try and do that.
Thank you, sir.
Thanks. Okay. If nothing else, thanks. Bye.